So at this point, we looked at some notation, namely that if we had a set and an element, we could write that that element is in that set and call it a day. But this doesn't mean much. What does it mean for x to be an A in terms of what is x equal to? So for example, suppose I had a set A is equal to 1, 2, and 3, okay? And I write that x is an A. This means that x could equal 1, or x could equal 2, or x could equal 3, right? Pretty straightforward. But what if we wanted to make a statement about that x? Then we need to be very specific about which elements in that set to which that statement must apply. Does the statement apply for only one of them, a unique one of them? Does there exist one of them? Does it apply to all of the elements in the set? For example, suppose I said that in my company, all trucks are subject to inspection. I may want to basically say, given the collection of all of my trucks T, for any truck T, lowercase t, that's in my bigger uppercase T, T is subject to inspection. But again, if I left it like this, then I'm saying, well, which T in T? What I need to do is use what's called a quantifier. A quantifier in respect to set theory basically lets us apply a statement about certain elements in a set. There's two basic, and there's a few more, but two basic ones we often use. You'll sometimes see this upside down symbol, A. This just simply stands for all. So if I say that all trucks in my company are subject to inspection, to write that mathematically, I would just say for all, which is the upside down A here, trucks T, where T is a single truck, and T is set equal to any of the trucks in there, then that T, for which it was set equal to, is subject to inspection. Now, this is different from saying there is a truck in my company that is broken. The question then is, well, which one? And how do we write that mathematically? Notice that it doesn't say, I can't do for all T in T, T is broken. I can't write this. That's not how I write that mathematically, because what that statement says is if I take any element from my collection of all my trucks, that element must be a broken truck. But that's not what that statement above here says. This says that there exists at least one truck that's broken. And the way that we can write this is with a backwards E. So when you see this in notation, this is just saying there exists a truck T, which is in my collection of trucks, that is broken. So notice how we represent mathematically two radically different statements. The first one says this statement needs to be true for every truck. The second statement says there needs to exist at least one truck. There could be more broken ones, but there needs to exist at least one. If we want to emphasize that there's exactly one unique truck which is broken, we would use a backwards E and an exclamation. And this stands for there exists exactly one unique truck for which is broken. That is how we use the language of logic. And yes, this is the language of logic to represent certain truths about our elements in our different sets. Why is this important? This is important because you're going to see this notation later in your education here. I might say, for example, I might want to make a statement about all of my trucks. For example, suppose the travel time R of truck I need that to be less than 5 minutes for all my trucks. The way I express that mathematically is that R sub I is less than 5 for all trucks I in T. That means this, if I pick a truck, the arrival time needs to be, for that truck, needs to be less than 5 minutes. So we use this language of math to shorten down our statements here about elements in sets. So again, the three quantifiers: for all, there exists, and there exists a unique.